Okay, my name is Chad Dubay. I'm from the University of South Florida, and this is my narration of the poster I'll be presenting on in person at Psychonomics, an application of statistical information theory to understand elements of short-term memory in the Atkinson-Shiffrin framework. So this, what this poster is about is a really simple question, I think. Basically, we have this very famous model of memory at a very large scale. Let's see if I can zoom. If I zoom. There we go. In figure 1 here, which is the Atkinson-Shiffrin model, and it just says if you're flying over memory from a great height, then it's going to look kind of like 3 boxes with some arrows. This would be, there are many modalities to this, and this would be in the visual modality. I am kind of implicitly on that in this poster because that's where I've done most of my research over the past 10 years. So basically, we all of us memory researchers have this in our DNA, our researcher DNA, I guess, now that there's a sensory store, a short-term store, and a long-term store. And the thing that has always interested me about this basic model is the way in which retrieval from long-term memory is thought to or assumed to activate some kind of related information in short-term memory. Now, in the 1990s, Shiffrin and Stivers, 1997, and then Shiffrin and various colleagues after that developed a model called REM, or retrieving effectively from memory. And that was building on earlier models and applying those earlier ideas to long-term recognition memory. And so basically, this is one of many research programs that have been stimulated by this framework. It's this REM model is within this Atkinson-Shiffrin framework, and it's describing one aspect of how this retrieval arrow is operating, what's happening during retrieval on a recognition memory test. Yep. And I'm not going to go in all the detail about the models. I could do that if I were in person, but there's too much variability in what people know and don't know, and you can always pause the video and go and read Shiffrin and Stivers' 1997 PBR paper. It's very clear, straightforward model. But it's also a very powerful model, and it's basically a global matching model that uses a Bayes rule to compute odds ratio. But the way it's done, it ends up being equal to a likelihood ratio. The ratio of priors cancels out. So that simplifies a lot of calculations. And the model produces a decision variable. In the original paper, it's called phi, which is a mean of all the likelihood ratios, in essence, supporting the idea that a probe on a recognition test is a representation when you're encoding it, is representing the same thing that a trace in long-term memory was encoding from a study episode. In other words, it's a way of saying that, yes, this is a representation of something I did in fact see earlier at study. And so that's a mean of all of the likelihood ratios computed from a parallel between the test probe trace and all the stored traces from the study episode. Okay, so that's used in the original model if you have an odds ratio exceeding 1, so you're anything, and I have no idea if this is old or new, then you'll say this is an old item. Otherwise, you'll say it's a new item. And but in other papers by Shiffrin and colleagues and then other collaborators, the idea that maybe maximum rather than the mean of these likelihood ratios could be the definitive quantity in the decision. And then yet another paper by Ken Malmberg in, I think, about 2008 suggested that actually we kind of upload a subset or a full set of and corresponding lambda values, likelihood ratios, into short-term memory prior to computing a mean phi. So basically, the question is, since this model says that when we retrieve from long memory, we have to activate something in short-term memory, the question is, well, now that we have REM, what exactly is REM sending to short-term memory? Is it phi, a subset, or a maximum of the likelihood ratios lambda? So that's the question. If you know, like I said, it's actually very simple question. The reason it took me so long to tell you about it is just because there's so much background about these models. And I know people will differ in what they know and don't know. Another thing that's proven especially difficult for me in talking about this research with people is nobody understands information theory. So I'm using information theory to do this, and there's a few reasons for that. One is I just think it's interesting. But the other is this is closely related to things that are happening in the short-term memory literature over the past 10 or 15 years. Specifically, almost all of the modeling work that's being done on things like the reproduction color wheel task and other tasks like that are assuming that you've got both fixed discrete slots that can be occupied by representations in short-term memory, well as some kind of resource that is limited. So there, in other words, many of the models on both sides of the debate about how to model this reproduction task, many, if not all of them, do assume that you have some kind of limit in terms of number of items you can store, whatever an item is, as well as a limitation in the amount of information about each item that you could be storing. In other words, the resolution with which the representation can be stored, how crisp are they, how much detail is there, something below the level of whatever an item is. And a few labs, Tim Brady and others, have explicitly linked this to information in a technical sense. It doesn't really matter if we uh, uh, which way you talk about it, because I'm going to show that in REM they correspond. So that claim holds up in REM. I'm going to show that resolution of a representation, which is controlled by the copy probability in REM, is directly related to information measured in bits, nats, whatever units you want to measure it in. Now, what makes this difficult about information theory is that there are people out there that think that they know all about information theory, and then when they review your paper, the only thing they seem to be able to functionally fixate on is communications theory. Claude Shannon. Claude Shannon did not invent information theory. Information theory was invented by statisticians before Shannon applied it to communication systems. And so I advise anybody, have a reviewer who's been following me from journal to journal who keeps saying this, if you think that logarithm of the likelihood ratio is not a measure of information, you need to read the many papers and textbook by Solomon Kullback, and you will see that this is a measure of information. It can be negative. It can be infinite. That's fine. None of that's going to violate the axioms of how information is defined in the technical literature. And everybody, if you go to the mathematical literature, this is like, duh. Okay, but in psychology, everybody wants to tell me this doesn't actually measure information, and the paper has been rejected at like 3 or 4 different journals, and usually the action editor repeats this phrase from this one reviewer who's been copying and pasting his review. So anyway, sorry if I'm salty, but this is the likelihood ratio. Everybody should know what a likelihood ratio is. REM uses exactly this formulation, just different labels, and they define it through the model parameters, but it's still a likelihood ratio. And Kullback showed that a log likelihood ratio, actually log of posteriors, is a measure of information. But in REM, the priors cancel out, so the likelihoods in the ratio of posteriors are the same. So you can take the log of the likelihood and you get exactly what he's talking about. Okay, so anyway, I'm going to use this measure because it's going to help in the derivations and it's going to help us see how REM is actually related to existing models in VSTM, which are dominant. And yes, there are people that will say, I disagree with that. But the reality is, if you read the literature, what the models are differing on is for this color wheel reproduction task, the measurement models. What they're differing on is details about whether precision is variable, whether you can share things across different slots. I don't think there's anybody, I could be wrong, but I don't think there's anybody saying there's only discrete slots. I mean, even if you go back into the literature in the 50s with the buffer model, I don't think you're ever going to see that. That it's only if people are just strongly committed to it's only slots. Okay. But anyway, um, so here's REM. For those of you that are not familiar with REM, it's just coming up with the likelihood ratio, the probability of the evidence, the set of matches and mismatches you get to stored traces, which are vectors of features, given that the hypothesis that the item was previously on the study list over against the hypothesis, the same thing, given the hypothesis that it's a distractor. So it's different from whatever you're matching to. And so this J here means for the jth trace, because remember, there's a whole bunch of traces in memory, and you're matching this test probe to them in parallel. So there are three alternative rules on considering what is getting sent to short-term memory by REM. One rule that's been proposed in literature is you send phi to STM. And there's phi. The second possibility I mentioned is that a subset lambda values goes to STM. And then these might be entered subsequently into some calculation through control processes. Maybe you're not conscious of it. I'm assuming you're not. It's a calculation of a phi value there. But the point is that there's a huge difference between just getting a phi into short-term memory and loading up maybe into a buffer, but still in the short-term memory system, loading up a bunch of individual lambda values. But otherwise, the calculation will end up being a phi. And so these two will be very, very similar. And if you're just looking at the basic calculation, the max rule would be a value of lambda goes into STM. And then so what I'm going to do is try to calculate the statistical information. Again, this isn't entropy. Okay, it's not the Kullback-Leibler divergence. It's none of those things. Those are expected values of information. Okay, this is much simpler actually, and it's totally accepted. Go read the books, go read the papers. These reviewers, I'm telling you, they just keep criticizing this for reasons that are just wrong. But the action editors never look. Anyway, so here's the calculation for the information that you would expect. This you can think of it as the amount of information favoring the item being a same versus a different image, favoring the first versus the second hypothesis. Again, because the likelihoods and posteriors are the same. So it doesn't matter which way you write it, really. So if you're sending phi, then you're taking a log 2 of just phi, which is kind of equivalent to just one lambda that's sampling distribution of lambdas and comes right from the center of that distribution, or actually from the mean, where the mean would be in distribution. The second idea that a subset of lambdas goes to short-term memory, that would suggest that you'd have information about every lambda value in short-term memory. So now you've got a perfect case for like using Jensen's inequality, because you've got a function of the expected value versus an expected value of the function. And we know they're not equal necessarily. In fact, there's a concave relationship, a nonlinear but monotonic relationship between the two. So they will not be equal, even though, as I said before, you could potentially have exactly the same value from this rule and from the subset rule. If you look at the details of the Malmberg model, it's possible to have exactly the same value, but you will not necessarily have exactly the same value for the information, because we're talking about what's being held in short-term memory. And then finally, the max value is really simple. You're just taking the neg log 2 of the maximum lambda value. So first thing, there's a whole bunch of things I'm trying to do with this to figure out which of these quantities is going to short-term memory. And they revolve around considerations of what seems plausible, what seems like it would work the best in a model, as well as what does this imply about what we should see in the literature, and then we compare that to things in the literature. So there are a bunch of theorems I've been trying to work on. I'm sure there are problems with many of them, but I tried to tighten a couple of these up just to show some of the ideas. So first of all, linking REM back to the slots plus resource idea, which is a lot of models of visual short-term memory. Assume you got discrete slots plus resources that are partialed out, and both of those are fixed and limited. Okay, so some people think that, and I'm one of them, that you could link resource limits to an informational limit, even though Miller showed that there's no informational limit, blah, 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 that there could very well still be one if your model isn't an exclusive OR, which is what Miller was using in his thinking. And the literature is now kind of accepting this. So the theorem, first theorem, we're gonna have a set S that's the closed and bounded interval 0 to 1, and C is in a subset, which could be a proper subset. C is the copy probability from REM, and we're going to take the image of the subset of lambdas through that function. So it's going to map, I guess, as an operator. And then this rule, so the theorem is, this is a bunch of buildup. The theorem is just saying that there's an informational capacity limit. There's a limit of bits or nats, or however you want to measure it, for activated sets A of lambda values. So look at the Malmberg paper if you're not sure what I mean by that. It's just a subset of lambda values, which could be the whole set. And then fixing the other, which are positive reals. This will hold. There'll be this capacity limit if and only if the least upper bound to the copy probability is between 0 and 1. Can't be equal to 1. That's the theorem. Okay, that's for this I delta of L rule. So then the proof is really simple. You just assume C is an open set versus assume it's a closed set, and take a limit up here. So if you're increasing C, of course, this is probabilistic, so the number of mismatches will jump, to make discrete jumps, but that's okay. I didn't put this in here. I should have, but because it's a proof after all. But as long as you're assuming that you get to the steady state on this before C reaches 1, so there's no more mismatches to be had, but C continues to increase, then you satisfy the precondition that you can always make a neighborhood around the limit point of C being 1, and the function will not have any discontinuities. So anyway, but it's pretty intuitive. So as C goes to 1, what's going to happen is you're going to have this quantity go to 0 in equation 1 over here for lambda. And this would be on either Lure trials or target match trials, because when you're on a target trial, you're going to have matches to non-target traces as well. So all you need is a non-target match. So it really doesn't matter if it's a Lure trial or a target trial. This is going to go to 0. And if this goes to 0, then I delta of X, which is down here, you can re-express as log of a product. And of course, you're going to have 0 times a bunch of things. So it'll be 0, and log of 0 is defined to be infinite. It's undefined. So that means the soup of the information in this case, as C goes to 1 on the leftward from the left, is not finite. It's not in the reals. So no limit in information. Conversely, we assume C is closed, then by definition, supremum of C less than 1, and it holds, and 1 is not a limit point of C, and that means the supremum of I is going to be in the reals. So that's all that this is saying, is that these are we're just proved that these two things are equivalent. So if if the maximum attainable copying value that a subject can possibly attain is less than perfect, then they are going to have a finite amount of information that they could possibly store, and vice versa. And we prove that equivalence by doing both the open and the closed set. So that's the first theorem. So that basically, in a nutshell, that links the copy probability in REM to resolution, and that should make sense, because better copying probability means more accurate vectors traces in your long-term memory and more features correctly copied down. That's why it's called C, correct copying. U might also play a role, but I'm not going to go too far into all this. So that links REM to slots and resources and shows that resources are linked to information in the sense of statistical information, not Shannon, not transmission, not George Miller. We're talking about statistical decision making. All right. The next theorem just shows that also for the other two rules, there's a capacity limit in information as well, and they're much easier to show. In fact, I won't even bother really going through this in too much detail. All you need to know, like for this first one, it just means, so you're doing the I delta of phi, the phi rule, then the information is I applied to phi. Well, phi is always real valued, and it's the I operator is just a log function, so that's going to also be real valued. So you know that I will always be real valued for, doesn't matter what the value of C is. And then for lambda max, you can run through what happens as C goes to 1 on a target trial, which is the case where the highest values of evidence could possibly be obtained is lambda max on a target trial. And that's going to, of course, put the probability of the data, given it's the same image, to 1, and that's going to limit everything to the geometric in the equation. If you look what happens, everything will cancel except you'll get a product of geometrics over and over again. So you take the log of the ratio, you got a log of 1, which is 0, minus the log of this thing, which is compounded over and over again based on how many things are getting multiplied together. So whatever it is, doesn't really matter. It's going to be some little value epsilon, but it will end up being real valued, and that'll be true no matter what C is, if you go to 1 or not. So basically, all three of them have a capacity limited information, although with the subset case, the sup of C has to be less than 1. So you have to have a closed subset that's a proper subset of the entire range of C. Okay, so those are just a couple of proofs they showed as capacity holds for all three. That doesn't really differentiate things between these three rules, so it doesn't help us with that, but it does help us to show we do have comparisons to benchmarks in the literature. It just doesn't end up distinguishing between the rules. So other things are more helpful. So like one thing is to consider whether there's a decision rule, whether the decision rule has a natural 0 point, because that was one of the things that were laudable about and talked about in the original paper for REM, is it had a natural fixed criterion point of equal odds. So it'd be nice if there's a natural 0 point in these different, in the informational side of these. The ID of L has no fixed 0 point, and you could see why that is if you look at this equation, that no matter what the phi ends up being, you're taking the sum of the phis rather than, or the sum of the log lambdas rather than the log of the sum of the lambdas. So this could be all kinds of different values that don't necessarily correspond to the criterion that you're using. In the phi rule and the max, there is a fixed point. So in the phi rule, you're responding old whenever phi is greater than 1. So if you take logs of both sides, then you got I delta of phi on one side and log of 1 is 0 on the other. And so anytime I delta of phi is greater than 0, you say old. So it's got a natural equilibrium. The max rule has an even more interesting one, because the max rule, as it's articulated in the literature, is respond with old whenever lambda max over n is greater than 1. So if you take the logs with that one, you get the information that corresponds to that rule would be I delta max exceeding log base 2 of the number of items that are in memory. So anyway, another thing to consider is identifiability in the models. So this is showing all the different kinds of mappings you can expect in the different kinds of models between an LTM subspace and the STM subspace. If you can think of LTM and STM as places, kind of like in Atkinson-Shiffrin, then T are the trace vectors, and they're giving rise to different lambda values from the matching, and those lambda values are getting turned into a phi value under the phi rule, and the phi value is what gets sent over here to STM. That's what this is saying. There are different ways in which this could play out, depending on how unique the mappings are to different things. So in this one, this is called a bijection from the subspace T, I'm calling this, to big lambda, where all the little lambdas live, in L, which is in big lambda. But you can see every t is uniquely mapped to one lambda, but then all the lambdas are summed up in this phi. So if we were going to try to recover any single trace from just a value of phi, that would not be possible because you got what's called a many projection from the space of lambdas to the space of phi, which I'm calling p right here. So anytime you have many to one mapping, there are proofs from real analysis and abstract algebra showing that this is impossible to get there, for there to be a function that would take you from here to here. If you don't believe me, go read one of those books. Yeah, you could create an algorithm like we always do with probabilities and sampling, but it would be nice if you knew like what gave rows to a given. Now that might not be necessary in a familiarity only model like original REM though, but that doesn't mean that that's what we want to stick with. Here's a version where you have that problem, plus you have the problem that multiple traces could give you exactly the same lambda value, theoretically. Might never see that, but it could, mathematically. Then in this case, we got the subset rule under similar kind of conditions. Here we have a bijection, have a surjection between the two spaces, and so in the surjection, you can't go from lambdas back to t, because you could have two t's give you exactly the same lambda, and you don't know which one to pick. And it would be nice, it would be desirable if you were looking at a test item and it felt familiar, that you wouldn't be confused about what that item was that you were reading. Like I'm reading the word bird and it looks really familiar. Could it be that I'm remembering seeing dog? That's why bird feels familiar. I mean, it seems like source retrieval isn't that absolutely terrible that that would happen. So, but maybe. So, and then finally, this is the same thing again, except for the lambda max. And so out of all of these mappings, the only ones where they're identifiable are model C, because it's a bijection, so an inverse could exist, and F for the same reason. The max value will be identifiable. You'll be able to identify a lambda, and from there be able to identify a trace in this case right here. So, and then there's some, I know I mentioned the VSTM literature, and I really only talked about a couple things from that, but there are other things I don't have space for that's related to research I have done over the years, having to do with ensemble coding and how reliance on prototypical representations of homogeneous feature, the stimulus homogeneous features, how reliance on such prototypes seems to increase the more similar and homogeneous the study items were to one another in those feature dimensions. And the only measure of information that behaves in a way that seems consistent with that is that I delta of the subset case. And also I have a proof that I think is correct. I don't think there's a problem in it, maybe. But that estimates of capacity could increase or conceivably decrease as similarity increases between the study items. And there's actually precedent in the literature for this. Shiffrin and Nosovsky had a paper in 94 or thereabouts in Think, Memory, and Cognition, where they talked about these ongoing mysteries about why capacity estimates behave in weird ways as you vary similar the distribution of features in things like absolute judgment, which we used to think was somehow separate from short-term memory, and now we think they're actually very, very similar and use many of the same processes. So anyway, this actually shows explains how and when that could happen within REM. So this full table, I jumped around, but so this is, there's a 0 point in this measure, not in this measure, and there is in this measure. So 1 means it can do this, and it's possible to do this. Not necessarily it will, but it's possible. Whereas a 0 means it's impossible. So there's no inverse in these two. There's an inverse is possible in this one. Well, it actually should be a 1 right here, though. So that's a mistake. But that's not going to change things very much in the conclusions. The capacity limit holds in all three for the information part of this, and that's directly linked to resolution, as we showed in REM. And this is what I just mentioned. And then finally, this is what I just mentioned. So basically, if you look at these three columns, if you had to pick a winner, you'd probably pick the max rule. But really, to cover all your bases, the best combination, the winning combo is going to be the conclusion right here, which is that REM, SEM, the maximum lambda value as well as a subset of lambdas to short-term memory. And that's based on just this, that would be my preliminary answer to the question. But of course, we all know that this stuff can change and there's a lot more to be done. If I can only get the reviewers to stop crapping all over this work just because they're so confident that they understand information theory, when it's clear they've never read Kuhlbeck's book called Information Theory and Statistics. Anyway, thanks for coming to see my poster, and I promise I won't complain so much if I meet you in person. And sorry for the errors and things too, but it's ran out of time trying to get things done today. All right, thank you.